Good afternoon. Welcome back to ECE 207. Exam number 2 minus 1, is that right? Exam number 2 is Thursday. Hopefully you will be ready. We're going to talk a little bit more about balanced three-phase power today rather than get into brand new material, and hopefully you'll be able to view this more as a review than jumping into chapter 14. But after the exam on Thursday, I would like you to start reading, if you haven't already read, chapter 14 and getting ready for that material, which is operational amplifiers, and we'll talk more about that obviously in a week when we return from our exam. This week, I'm not sure what happened, but I'm offering more office hours. You're going to have 2 periods tomorrow, that's Wednesday, available to you. The normal time, 9 to 11, an afternoon slot from 1:30 to 3. All of these will be in the same room, ECE 523. And Thursday, if you have last-minute questions, hopefully you're not just starting to study for exam number 2 at 3 p.m. or 1:30 on Thursday when the exam is at 3:30. I will lock the door at 1:30. Actually, I have things to do beyond that time right before the exam. Homework number 5 should be due. Hopefully you have turned that in or will turn that in. I wouldn't spend all of your time frantically trying to finish that up this hour. Hopefully the lecture will be better than the homework. No, I don't know. But you only maybe get this once. Hopefully this one is being recorded. Review material for exam number 2 is on D2L site. It's near the bottom of the page, of the content page. I work through quite a few problems, and I do some other things like complex impedance, complex math, etc. at the bottom of that page, hopefully to help. Today what I want to do is go over three-phase power, look at this conversion from phase voltage to line voltage. Maybe that isn't even clear yet as far as the terminology. Hopefully the terminology will become clear as we explain it. Then we'll look at a balanced Y-Y connection, which is really what you had on your last problem for the homework. Hopefully now it will make more sense. Did I go dead? That was Yes, I ran out of battery power, and this is an electrical and computer engineering class. Is that what you were just saying? Somebody put the clip on a dead battery. That was the problem. Maybe. I don't know. Maybe that's why it was on the desk. We'll see if this one lasts more than 3 minutes. Is that what it was? Oh, yeah, probably. It's at 3:34 right now. We'll get into line current, single-phase analysis, or how, when we have a balanced three-phase system, we can actually pull out and only work with a single phase, and that really gives us all the interesting information. The other information we can obtain by simply subtracting angle from the phase. It's all going to be balanced, and so the line currents, the line voltages or the phase voltages, those will all differ by 120 degrees. Not that they will all be 0, minus 120, and plus 120 all the time. They would be if you had a pure resistive load. If you have a load that's not purely resistive, the current could be different than the voltage phasor in terms of the angle of those phasors. Hopefully that's clear, and you need to know that for the exam. Let's look at this three-phase voltage, or I should say balanced three-phase power system. In this class, we're really concentrating on a set of loads that are balanced, that are three phases, and a set of sources and the interconnection. And we'll talk about the different possible interconnection structures today. We've been concentrating so far on the Y-Y connection. The first in that Y-Y is the source. The second Y refers to the load. In this case, it's saying your sources are connected in a Y configuration, your loads are connected in a Y configuration, and those two subsystems, sources and loads, are interconnected with lines. In a Y-Y connection, we have Y sources, and those Y sources are connected from the high side to the neutral. Let's say that's the A phase source voltage, and that last time I think we were calling V sub phi. That was the common magnitude for all of these. And the A phase, a lot of times we do reference at 0 degrees phase. This might be then the V sub A phasor. We also have the B phase and the C phase. And notice their negative terminals are all connected together at the common node or the common neutral location. This is now behind the A phase by 120 degrees, and the C phase, so this is V sub B, the C phase, let's say V sub C, is behind the B phase by 120 degrees, which makes it minus 240, but typically we keep our angles between plus and minus 180, and 240 is the same as, minus 240 is the same as plus 120 degrees, meaning the C phase is behind the B phase, because we're rotating in this counterclockwise direction. Here are the lines then that feed or go to the load. Last time I think we hurriedly went through the relationship. So this is now a phase voltage, and if we really wanted to get more specific, we would say a source phase voltage, and that's the A phase. But they all have the same magnitude. They all differ in angle by 120 degrees. That makes them balanced. The fact that they differ each by 120 degrees and that they have the same magnitude. That makes them a balanced set of sources. What we might be interested in is measuring with our, let's say, multimeter this voltage V sub AB between the A line and the B line. The phase is from the line to neutral. The line in this configuration, in this interconnected structure, is between line to line. Question? The question was, if I think this is rephrasing your question. You're saying, you know what, if I visually do a KVL around that with an air gap including VAB, that will give me VAB, and it looks like one is subtracted from the other, and they both have the same magnitude, so why isn't that 0? It's because they aren't quite aligned in angle. One is behind the other by 120 degrees, and if you looked at their time waveforms, they would not overlap. They wouldn't be in phase. They would be out of sync in time, and they're out of sync in time by that minus 120 degrees. So I think you answered your own question, but you were asking, right? Is that what you were asking? Did everybody understand that? If we try to find VAB, I would maybe try to find that by just writing a KVL equation relative to that air gap between the two lines and then coming down through V sub A and V sub B. Meaning if I now want to define V sub AB as a phasor, I would say, well, let me start here and go that way around this loop. I can create a loop or a mesh anywhere, and it can include an air gap. It doesn't have to have an element in that loop. Meaning, going around in that manner, I would say, well, I'm entering the minus terminal on AB. So there's minus V sub AB, phasor. The next thing I come to is actually the positive terminal of the A phase voltage. And so I now have plus V sub AB. I'm sorry, plus V sub AN. And then I come down through V sub B through the negative terminal, which is really minus V sub BN. Maybe I'm getting sloppy and just calling those V sub A. Maybe I should call those, double subscript those, and say that's V phasors sub BN, sub AN, etc., to make it a little bit more clear. Any questions on where that came from? This was simply from KVL. And you need to be able to do KVL. We're going to be doing that all semester. Even when we get into operational amplifiers, you need to get comfortable with KVL and doing it across air gaps. Question?
VAB, I saw that you had negative VAB and there's a negative charge. Does the negative always start at the bottom?
So the question is, does the negative always start at the bottom on a label of a voltage? And the generic answer is no. This is just how I decided to label mine. I wanted to consider the A line more positive than the B line. If it ends up being negative, it will become negative. If I had a voltmeter, this now tells me that, oh, I'm actually putting the positive lead on the A line and the negative lead of this voltmeter to the B line. Does that make sense? I could just as easily flip those measuring leads, and then I would have been measuring V sub BA. And it should be the negative of what I measure here, obviously, I hope. If it's not, then I would start to question what I was doing, or my meter, or I would start really wondering what's going on. Question?
You said this was balanced, and that was because they're each separated by 120 degrees, and something else they were...
The reason these phase voltages or these sources are balanced is because they're separated by 120 degrees and they have the same amplitude. So that's V sub phi. And I'm trying to emphasize that by just calling them all the same magnitude, V sub phi. And that I didn't even say, but I'm assuming that's RMS in this case. Meaning the A phase has an amplitude of V sub phi at an angle of 0 degrees. If I said, what is V, this is as a review. If I said, what is V, little v sub AN of time? What's its time domain expression? What would you do on the exam? Not drop back and punt. Do you need more information? Do you need more information? And if you do, what more information do you need? You need to know whether you're in the United States or Europe, right? And I thought I might have a visitor here from Europe today, so I was a little nervous. But it's a little late, I guess, in the day, and never mind. I don't think he's here. If he is, he's leaving early, probably. What was I doing? Oh, frequency. So, yes, you need to know whether you're in the United States or Europe. And I'm going to assume, and that's not even all. You need to know, is this coming out of the wall? Or is this coming from a power company? Or is this some made up in a lab system with a frequency of maybe 20 radians per second? You don't really know that, do you? So you should say, when solving this, I am assuming a frequency of 60 hertz. or that translates into an omega of 377 radians per second. I'm assuming a frequency of omega equal to 377. Is that?
You said we have to be comfortable with KVL with an air gap. Couldn't you just use that to make the voltage across any point 0? Because you could do an air gap, like do a pretend wire around it.
Well, maybe I didn't really explain what I'm meaning by an air gap. I'm just going from this, I'm wanting a visual, this line to that line, and that difference in potential, if I could hook up a voltmeter to that, that's what I'm considering an air gap. But there's a potential difference between those two lines. That's all I'm meaning when I say an air gap. There doesn't have to be a circuit element. Actually, there was a resistor between those. It was me. 100 ohms, about 50 ohms, and 100 ohms. And hopefully there's not much going through that. And I've already told you, well, yes, there's something through here. I meant current going through here. I don't want any current passing through the trunk. Okay? That's not a good thing. Where were we? Have we returned from Europe? Question.
Yeah, so what's the right answer?
I don't even know what the question is.
Phasor and time.
Pardon?
Phasor and time.
Oh, the phasor and the time domain. Thank you for getting me back on track. What is the answer? Any help? I know what omega is. I'm going to assume that's 377. So I'm assuming omega is 377 what? How could I give you 0 points if you just put 377? You need to give me the units. Radians per second. So that's now radians per second. And that's going to go in here. This is the A phase, and I assumed it was at 0 degrees phase. And we're calling our phasors cosines. And if I look back, V sub phi is squeezed in there somewhere. Am I done? I was assuming the V sub phi was an RMS value, and so the maximum value on your time domain waveform is the square root of 2 bigger than that. This, in terms of what I'm assuming, is this particular magnitude is expressed in RMS units. That's typically assumed when you're talking power. That was not a part of this problem, but it was a good review for the exam. Other questions on that? That all started with, are we comfortable with KVL? And now you're going to quickly go, yes, no more rabbits, right? Don't chase anymore. This equation can now be used to solve for the line voltage VAB. If I put it on a side by itself, I now have V sub AB is V sub AN minus V sub BN. Those are subtracted, but remember, those are phasors or vectors. And this is now a vector subtraction. V sub AB, and we did this before, didn't we? V sub AB was V sub phi at an angle of 0 degrees. And we subtract from that V sub phi at an angle of minus 120 degrees. V sub phi is common to both of those, and I can now say something like this. Is that okay? I just factored out the magnitude, and I explicitly tried to indicate that that is a vector. It's a magnitude 1 at 0 degrees, and I'm subtracting from that a magnitude 1 at minus 120. in this form, you should be able to convert that to rectangular form. And that could be a gift Thursday. If I give you a complex number in any form, you should be able to give it to me in another form. Everybody should be ready to do that. This is polar form. I could say, well, polars are kind of hard to subtract and add. It's easier when they're in rectangular form. Meaning I would convert this to rectangular form, or the 1 at 0 degrees is all real. Doesn't have any imaginary part. There's no angle. Well, there is an angle. It's 0 degrees. The other angle is way back at minus 120, and that does give me a real part and an imaginary part, and it actually gives me a negative real part. Meaning, in terms of vectors, this looks like that and that. So here is 1, and here is 1 at minus 120. And I'm actually subtracting those. Meaning, if I want to subtract those, I could just flip this one. This is now minus 1 at minus 120. And to add these two vectors, I can simply make up this parallelogram, and that's actually my result of adding those two vectors. Question?
That V, that's RMS, right?
V sub phi is RMS, and that's common to both, so I factored that out. Whatever I get for that blue vector, I'm scaling by V sub phi. V sub phi is a number. That might be 120 if it's coming out of the wall, for example.
Isn't that the same?
Question?
Is 1 at negative 120 degrees vectorially the same as negative 1 at...
Oh, I'm sorry. I didn't, well, actually that's okay the way I've written it. 1 at minus 120 is the same as minus 1 at minus 120. I've just negated that, so it should just flip it in behind itself. It should just reverse direction and go in the opposite direction.
But then shouldn't it be at 120 degrees?
Well, minus 1 at minus 120 is equal to 1 at the 180 degrees from that. So if you add 180 to minus 120, what are you going to get? 60. So this should be 1 at 60 degrees. This guy right here. This should be 1 at 60 degrees. Is that making any sense? The sum now of 1 at 60 and 1 at 0 is my resultant, which maybe if I had drawn it better, let's go back. Here is a figure in the book. This is what it should be. This is figure 540 in your textbook. Here is V sub Bn. That's V sub phi at an angle of minus 120, and here's V sub An. We negate this guy, and that flips up here. That's where that minus sign comes from. And now we're just adding V sub An to minus V sub Bn. And the addition of those, you could either form this parallelepiped and get the diagonal, or you could go, you know what, let me do them head to tail. This is now minus V sub Bn, and the sum of those two gives me V sub An. That shows you, I hope, that V sub AB is longer than either V sub An or V sub Bn. And it also gives you the angle. It gives you the 30 degrees. That's splitting that 60 degrees in half. And the length you can find by trigonometry. Didn't we find it last time to be the square root of 3? That's the way that these line voltages, if we go back, and another way of looking at that is in this picture. Here is V sub An, here's V sub Bn, which if we subtract that, it would be coming down here. And now that particular line is going to be that in magnitude. There's your VAB, if that's easier for you to think about. You now have these phase voltages inside these bigger line voltages. And that's figure 541 in the text. That's just a way to view it graphically. If you didn't like doing it analytically, which is to say, oh, V sub AB is V sub phi, and this is 1, and now I'm going to subtract from that 1 times cosine of minus 120 degrees plus J sine of minus 120 degrees. Cosine of minus 120 is the same as cosine of 120. That's a half. So this piece, actually it's minus 1/2. It's left of the origin. It's now minus 1/2. And this piece is square root of 3 over 2, the 0.866, or the 0.867. Meaning we now have V sub phi times 1.5 minus J square root of 3 over 2. Actually, this is a minus. I didn't do that there. The sign of minus 120 is down below the axis, so there's a minus sign, and a minus gives me a plus. I now have 1.5 plus J square root of 3 over 2. If I now converted that to polar form, you would have a magnitude of this, 1.5, 15 squared. It's 2.25, isn't it? 225 is 15 squared. Square root of 3 over 2 squared is 3/4. And this angle, if you compute it, is the square root of 3 over 2 all over 1.5. Or the square root of 3 over 3, or 1 over the square root of 3. This is now V sub phi square root of 3. That's the magnitude of this line voltage, and this is 30 degrees, which we found graphically before. And this is our line voltage. And its magnitude has now been increased by this square root of 3 factor. Questions on that? So if we wanted to measure that line to line, it's obviously bigger than the line to neutral or the phase voltage in this Y-connected source configuration. Question? Now that we have that knowledge, let's go ahead and connect that source to a set of loads. If we have that source connected to a set of loads, and let's assume that these are all the same, and I'm going to call those Z sub Y's because this load is balanced and it's connected in a Y configuration. This is my A terminal, here's my neutral. Over on the load side we use capital letters. Here's capital B, here's little b. And there's little c. The c's, I'm sorry, are maybe going to be confusing, but hopefully you know that that one on the left is a lowercase c and that one on the right is an uppercase C. I'm not sure what font either one are in. Questions on that? What's the angle of the B phase voltage? Minus 120. Because I might be that vague on the exam. I might say you have an ABC or a positive phase sequence, three-phase set of sources. That should immediately tell you what you have here, if I just give you that description. This, it's either a positive phase sequence, or I could say an ABC phase sequence. So this is a positive phase sequence, or it's an ABC phase sequence, and now I'm going to mess up my diagram. But ABC is normal or natural. That's why it's called the positive. If it was an ACB, which we're going to get to later, that would be a negative phase sequence. If you understand the positive phase sequence, that's enough for this class. But I want you to know that there is a possible, another way of running these machines or these generators. Now I'm going to connect this A phase terminal on the source side to the load side. I'm going to connect my B phases, and I'm going to connect my C phases. And in case that rabbit we were chasing got caught and shorted something out, we want that current to go somewhere. We want it to go to ground. And so we're going to have I know, I shouldn't have said that. Normal, we have a line on the neutral. Okay? Please don't be picketing before the exam. Now what can we do with this? Now we have current flowing in all of these. We have a current going from the source to the load in the A phase, and that would be our line current, and I might even say that that's the A phase line current. But from that you should be able to immediately see, well, I could draw the B current and I could draw the C current. Label them in that way. If you didn't even know this material, I could argue that you still know how to solve this problem. You've had the first half of Chapter 5. It's power. Or you've had the sinusoidal steady state material. You now have the information to solve this problem. You could solve that as a three-mesh system, couldn't you? You have the top mesh, the middle mesh, and the bottom mesh. That was MESH, not MESS, if you were listening. Sorry. So we're dealing with mesh currents, okay? Not a mess. This is beautiful. All in the eyes of the beholder. So we have the B phase line current, we have the C phase line current. Those are actually, if we have a balanced set of loads, and those are balanced because they're equal. The A phase has Z sub Y, the B phase has Z sub Y, C phase has exactly the same. We're assuming the loads are the same in all three phases. That's a given. This is now a balanced three-phase system. In that particular, so we're assuming, well, we're giving ourselves this balanced three-phase loads, meaning Z sub A is this Z sub Y, which is Z sub B and Z sub C, which I guess if I wanted to go with a little bit more notation, I would say A sub n, A n, Z sub B n, etc. What else have I not included? I haven't included what this particular current is, let's say I sub n. Or it could be I sub capital N little n if we wanted to use the same notation. How could I find I sub capital N little n in that picture? You already know how to solve it. There's a node, isn't it? The algebraic sum of the currents at that node, you can't have current accumulating at a node, can you? KCL has to be satisfied. At that particular node, we know the currents leaving that node are in the neutral line. The currents entering are all coming from the three different phases. We know in that particular interconnection by KCL, we have I sub n is equal to I sub AA plus I sub BB plus I sub CC. But since this is a balanced system, we know all of those currents are related to each other, just like the voltages are related to each other. The voltages are related to each other by 120 degrees. The currents are also related by 120 degrees, and what their angle is depends on the impedance of one of those load phases, Z sub Y, and those are all the same. If I now know that the system is balanced, which it is, you know that you have your sources are balanced and your loads are equal, and if we're told what the A line voltage is, I sub AA, suppose somebody says, you know what, that's I at an angle of theta. If you know that, and you know you have a balanced system, you now know what I sub BB is and what I sub CC is equal to. Anybody want to tell me what those are? So this is now the same magnitude, isn't it? We know they're going to have the same magnitude since it's in a balanced system, and this is 120 degrees behind the A phase line current, and the C phase is 120 degrees ahead of that theta angle, and the theta is going to be influenced by the impedance of the load. Suppose I said Z sub Y was a resistor, a pure resistor. What would theta be in this example?
So if we're given the balance, then we know that the current in the neutral line is zero. That's the conclusion we can draw.
Did anyone hear my punchline? The question was, if we know it's a balanced system, then the current in the neutral is zero, and the answer is yes. You answered your own question. You didn't even ask a question, you stated the fact. And that's what where I was going with this.
But doesn't that what the balance means?
Yes, that's basically what the balanced means, is we do not have any current flowing in that neutral conductor. And now let's show why that's true. We've now, I hope, you now feel okay with this relationship on our line currents. If, and this is just going to help me sketch the picture a little easier. If I assume Z sub y is R, then this theta in the above current is 0 degrees, meaning my current is in phase with my voltage. And I don't have any impedance on the line. That's an assumption. But in a real system, relatively speaking, the impedance of that line from source to load is negligible compared to the load. So we're going to just neglect it and assume that we just have a pure, ideal, non-resistive wire between source and load to give us a feel for what's going on. If that's the case, then we have this line current, I sub AA, here. We have I sub BB here. So here's I sub AA. These are all supposed to be the same length. This is I sub BB, and I sub CC is there. If I add those all up, head to tail, so the head of A gets the tail of B, and then the head of B gets the tail of C, I'm going to end up with that, and these three that have formed my triangle are the right-hand side from my KCL equation. And what I'm trying to show you is that the current in the neutral conductor is 0. Questions on that? If I go back to my diagram, and if I have 0 current flowing in that conductor, the neutral conductor, if there's no current flowing, what's the voltage difference between little n and capital N? 0. There's 0 potential between those two ends. The little n and the big end have 0 potential across them, or between them. If that's the case, what does that mean? You could theoretically connect them, right? It's the same potential. That's the same point. Little n and big end is the same point. You could theoretically connect those. If you connect those, now you know exactly what voltage is dropped across your A-phase impedance, correct? Is that making any sense? This is actually allowing us the ability to simplify your analysis. Instead of doing those 3 mesh problems to find I sub AA, I sub BB, and I sub CC, we can just extract one phase, solve it, and then knowing that it's balanced, we can just adjust the angles of those line currents to obtain the B phase and the C phase. Let's do that. We have a balanced 3-phase system, or in general, balanced 3-phase systems can be analyzed via a single phase, let's say piece or sub-circuit. Meaning, because it's balanced, we can now extract any of those phases, and let's use the A phase since that was our reference phase and the angle was 0. Now we can, all we really have to analyze is that particular system, and I hope by this point in the semester that's a gift or a piece of cake, whatever you prefer. Either you want a present or you're hungry. You should be happy. That should bring smiles to your face on Thursday if I gave you such a gift or a piece of cake. Probably won't feed 150 of you on, but implicitly I might. Okay? What is the line voltage? Now that I've made such a big deal about this being a gift, don't disappoint me. It's the A phase voltage over the A phase impedance, isn't it? Or it's V sub phi at 0 degrees over Z sub y, whatever Z sub y is. Z sub y could be inductive. What does that mean about the load, Z sub y? Current lags, that's good. If I said, give me a load that is inductive, what would you give me as far as an expression for Z sub y? You would say J omega L. Oh, but I'm assuming, so I wasn't very clear. You could say, well, I'm assuming you have some real component. So you would say R plus J omega L, right? Or you could just as easily say something like, well, let's let ZY equal 4 plus J3. That would be an inductive load, right? If I didn't give you anything more, you could say, oh, well, that's an inductive load, or this is an inductive load. All of those are inductive loads. Why? Because the J term is positive, and that's what we have with an inductor. If it was a capacitive load, then the sign of that imaginary part would be negative, because it's 1 over J omega C. The J downstairs, when it comes up, becomes a negative J. Question? You were just stretching? Sorry. I need some exercise, I think. Questions on that? Everybody get that? Is that what you had to do for your homework problem? What if I said, what's the power of that load, of the three-phase system? What would you do? It's balanced. Okay, you could say, you know what? It's balanced. Let me find the power in one phase and multiply it by 3 or add up the 3 pieces, right? Either one should be equivalent. And the easy answer is probably multiply by 3, the total power. So if you wanted the complex power of the total, I might say, you know what? Let me find the complex power of the A phase. And we've listed several of these. In this case, we had no impedance between the source and the load, so the voltage across the load is the source voltage. So this would be V sub AN. What would I multiply that by in order to get the complex power?
Complex conjugate of I.
We would have I sub AA. That's our phase current, or the line current in this Y configuration. And that would give me the A phase, the total complex power, since it's balanced, would be that. Questions on that? And from that, you should be able to give me apparent power, which is magnitude of that number, of that vector. The real power is apparent cosine theta, right? Or apparent power times the power factor. Two ways of thinking of that, but the power factor is just cosine of theta, and we're assuming you find theta from that. And the reactive power, its units, VARs. What are the units on the real power? Watts. The units on the apparent power? VAs, volt amperes. See, you guys are getting ready for exam number 2, right? Question?
Why did we just sum it up if this is
I'm sorry?
Why did we just say 3?
Why did we say it's 3?
I mean, we can just assume it's balanced.
Well, it's balanced, and what did we just determine, or I tried to convince you, there's no current flowing in the neutral, so now let's justify why we could scale that. Actually, we wouldn't have had to. We could have said, you know what, I don't believe him. If you didn't believe me, what would you do? You would add them all up. You would do what was suggested before. You would say, give me the A phase complex power, give me the B phase complex power, give me the C phase. I'm going to add them up. There's your total power. If you do that, I think you would find, well, you will find that that's actually 3 times one of those phases, complex power. Because what's the B phase complex power? Same thing as the A phase, isn't it? Magnitude. They just vary by 120, but both parts vary by 120, meaning their voltage and current both are shifted by 120, so they're in the same relationship as the A phase relative to each other. So the B phase is the same. The C phase you'll see is the same. So that's why we multiplied by 3. Does that convince you? Any more hand waving? But hopefully that was more than just hand waving or saying some magic happens. Hopefully now you're starting to see where that would come from or how that would happen. Other questions? Now if you go out and get a job in some company that's maybe using a lot of power, or you're delivering power to some other customers, you now at least know something about 3-phase power. There are some variations. What are some modifications? But you really know a lot relative to power. Modifications on this one concept. I could say, well, actually, we are working in our plant with a negative phase sequence. Maybe that's what you're told on the first day. Then you just go off at lunch and you, on your napkin, start making a sketch. Right? Sure. That's the answer I'm looking for. Just be a little bit more positive. Oh, you're negative. That's right. I'm sorry. We're talking about the negative phase sequence. So you were trying to be a little more negative, weren't you? I understand. What is this? What's the positive phase sequence? No, the positive phase sequence doesn't have to be inductive. It could be capacitive. It could be either. The positive phase sequence just means the relationship between the A phase, the B phase, and the C phase. And you know if you're standing here watching them spin around you in a counterclockwise fashion, A is going to hit you first, B is going to be next, and C is going to be last. That's a positive. If it's negative, it just changes B and C, meaning now you have an ACB. So negative means not Sesame Street, right? If the positive was ABC, this one's now not that. It's ACB, meaning if you needed to sketch this on your napkin, you have a negative phase sequence, you're going to sketch some pattern like this, where that could represent voltages or currents. But if you're standing here, then as these are spinning around in a counterclockwise fashion, A, C, B, A, C, B, A, C, B, that's how they pass you or go by you. And in this case, then, for a negative phase sequence, we might still keep this as our reference at 0 degrees, but now, what do we know? We now know that V sub Bn is what? It's now V sub phi at plus 120, and V sub Cn is now 120 degrees behind the A phase. That's a negative phase sequence, and that's a possible modification. They may just have their machines interconnected in such a way that what they've labeled the A phase, the C phase, and the B phase, it's circulating as ACB, ACB. But you know how to analyze it. You analyze it just the same, except you just have to keep track of this relationship between the B and the C phase relative to the A phase. Not a big deal. Another modification, this one's a little bit more interesting. That's delta. That was supposed to be a triangle. That's a delta, and now that I've gone over it 6 times, it's going to erase it. But we now have delta connected, or the possibility of having delta connected sources and or loads. Suppose I have a delta-delta system. What would that look like? That now, let's sketch. Now I have actually, and this is where it could be confusing. Don't let it get you too confused. Maybe it's not confusing at all. Let's label this A terminal, B terminal, and C terminal. This is now V sub AB in a delta configured source. That's actually my line voltage. It's also my phase voltage in this configuration. So if that makes sense, don't even listen or don't pay too much attention. But the phase voltage in a delta connected system is actually the line voltage. So they're the same. So here's my sources, and now these actually are, here's V sub BC, and which way do you think the polarity, and if this is now V sub CA, what's the polarity marks in that source? Which polarity mark goes higher on the page? We have a 50-50 chance, or is it none of the above? How many think it's negative? Everybody have your clickers? Are you clicking in, getting credit for this? How many think it's positive? It's minus. So now it's plus minus, plus minus, plus minus. It's now V sub CA, so C is more positive relative to the A terminal. It's just the notation and convention. Now we have a delta connected set of loads. And if we want things to be balanced, then what do we know about V sub AB, V sub BC, and V sub CA? If those are balanced sources, they would all add up to 0 if you strung them in a row or in a series connection, which they're not. They're connected head to toe. But what does that mean? This is now, I'm talking to sources. Pardon? they're still 120 degrees out of phase, aren't they? And the magnitudes are equal. That's what it means when we have a balanced set of sources for a three-phase system. They're 120, those 360 divided by 3 gives us this 120. Now we just need to connect the sources with the loads. And that's a delta-delta system or interconnected system. A delta set of sources and a delta set of loads. And you can analyze this with your knowledge of sinusoidal steady-state behavior. Right? What do you know is happening here? What did somebody just tell me? It's 0, isn't it? So that's trivial, that mesh. Let's not even worry about it. If we summed up those voltages in that loop, we would come up to 0. Their sum would be 0. So the more interesting meshes would be, let's say, this one and this one. If it's balanced, we know this guy is going to be 0 also. I should have done those in different colors, shouldn't I? The ones we want to neglect. What color is this going to give me? Oh, I feel like I'm in art class. Yellow and magenta give me red. I know that by my color triangles. And I'm dealing with triangles because I'm talking deltas. Oh boy. You can't wait for a test. That's why I'm doing this. You want to just anticipate exam 2 because I won't be lecturing. How's that? Exam 2 is Thursday. So those red meshes are 0. The only 2 meshes you would have to worry about are those 2. Well, you could actually do an outer mesh if you wanted to, all the way around the perimeter, and that would give you the C-type phase, wouldn't it? But what does this one tell you right here? Little a and big A, that's a pure line, or a wire, isn't it? Little b, capital B is a pure wire. We know exactly what the voltage drop across that Z sub delta in the AB, across the AB line is. It's just V sub AB. So in this particular configuration, if I wanted to know, and now what becomes more interesting maybe, might be these particular currents. This phase current in the load, I sub AB, I sub BC, and I sub CA. Those might become more of interest. And I sub AB is what? Is it clear that that's V sub AB divided by Z delta? Does that make sense? What if I just made some assumptions? Suppose that V sub AB I said was 10 at 0 degrees, and suppose somebody told me that Z delta was 4 plus J3. And now you need to find the value for I sub AB. And if I say find I sub AB on the exam, I probably do not want it left in that form. I probably want it cleaned up a little bit, meaning a complex number, not a ratio of complex numbers. I either want this I sub AB as a rectangular complex number or a polar form of a complex number. How would you do this to clean it up?
You could multiply by the conjugate
You could multiply by the conjugate of the
Denominator.
denominator. I didn't get a lot of support for that solution, but did everybody hear that? It's true. You could multiply by 1, couldn't you? You could multiply by 1, which is 4 minus j3 over 4 minus j3. That's the one you would want to multiply. That now basically cleans up the denominator and makes it completely real. And then I wouldn't be opposed to that answer. Downstairs you have 25. 4 squared plus 9 squared. 4 squared plus 3 squared, or 16 plus 9. Question?
So you could leave it with the polar and the.
No, I'm sorry. I want you to multiply this out. Well, actually, I guess this tells me that you know what you're doing. So if I was not a computer, but you have to remember my first name, so that doesn't work. Sorry. I never liked that joke anyway. But that's what you get, right? Real part squared plus imaginary part squared, which is 25. And upstairs you have 40 minus j30. Or you now have 40 minus j30 over 25. And what do we have? 8 over 5 minus j 6 over 5. Did I do that right? Is that right? So this is now is that true? That's one way of writing the answer. What's another way? I would have probably converted the denominator to polar form, which the magnitude of, that's a 3, 4, 5 triangle, that's 5, and then this is the inverse tangent of 3 over 4. That's something smaller than 45 degrees. It's the 36.8 one, isn't it? So this is now 2 at an angle of minus 36.87 degrees. And that should be consistent with the 1.6 minus j 1.2. Either of those answers is correct, but that's what I would be looking for. Questions on that? That's now my phase current in a delta connected load. If I ask you for the total power in that system, what would you do?
Find the power of the one part and multiply by 3.
So here I'm saying the total power. You just said, I think, I would have this is 3 times S, let's say A. And what was S sub A? Is that true? And V sub AB and I sub AB with a conjugate. Or this now in terms of a single phase is 20 at 36.87 degrees. And that's volt amperes. And I now know the apparent power and I know my power factor. Indirectly, I know my power factor. What is the power factor? I'm sorry? Are we okay? And is that power factor leading or lagging? Why was it lagging? It was a positive angle, wasn't it? It's going up. Our Q is positive. It's inductive. And we could find the P and the Q for that single phase. We now know that the total apparent power is 3 times 20 or 60 volt amperes. That's our total apparent power. What if I gave you Y loads, Y connected loads, and a delta connected set of sources and said analyze this? It'd be nice if we could relate the different delta connected loads. Here's the little picture to help you do that. Here's delta connected or here's Y connected loads. Those are all the same, and those are ZYs. That's the red. That should have been a triangle, but my picture is lacking. That should look like, is that a Superman symbol? I don't know. Which one is inside or which one's beyond the other or outside of the other? If those are all equal, that picture showing you that the Y is inside the triangle says that if you needed to convert from one form of a connected load to another, and if they're equal and balanced, they're related by a factor of 3. And which one is bigger? Well, you remember this picture. You draw that on your napkin. You put down this triangle and you go, okay, does a triangle go outside or inside a Y? It's easier if the Y is inside, right? Or I guess an upside down, well, that's the Y configuration. So I now know that if somebody gives me Y connected loads, I can convert those to delta connected loads if I want to. Or if somebody gave me delta connected loads and I wanted to convert those for analysis purposes to a set of Y, then I could do that by that picture. Question?
Are we going to see any delta loads?
You probably will not see any delta loads on the exam. Keyword is probable. No, I don't think you're going to see delta. I don't think. I always hedge my bets. I'm not planning on that happening. Okay? But I'm trying to give you a little bit more information so that if somebody starts talking and saying, well, I have a delta connected load, you go, well, I never studied delta connected loads. At least you know a little bit about the concept, the idea, and it doesn't completely make you nervous. Question?
On the test,
We still have 2 minutes. What?
are we going to just be able to use phasors, or do we have to actually be able to do differential equations?
So on the test, do you have to do more than phasors? And the answer is yes. You need to do first order differential equations, which is chapter 4. So the material that you'll be required to know on exam 2 is chapters 3, 4, and 5. I may try to put a little study guide, just a list of the topics, but it's basically those chapters. What homeworks have we had? 3, 4, and 5 homework sets. I'll try to post homework 5 solutions. There are already worked problems on D2L at the bottom of the contents page. Question?
Is any particular chapter going to be tested more than any other?
No, I don't think any particular chapter will be tested more than another. It's going to try to be fairly uniform, although chapter 3 there may not be as much to get you with as 4 and 5. But I think you know that.